Hi, this is Matt McCormick. I'm in the Department of Philosophy at California State University, Sacramento. My email address is mccormick@csus.edu. This is part of a series of lectures for my Inductive Logic Phil 61 course. We are now in Chapter 4 of Ian Hacking's um, Introduction to Probability and Inductive Logic. This is my first lecture on that Chapter 4, and we're going to introduce some basics about probabilities. So let's get a little clearer on what a probability is. There's actually some disagreement. There's two ways to talk about probabilities. Um, we're going to run these together. It's not going to cause any problem. It's going to work fine for us. We can treat these two the same. But we might talk about the probability that a proposition is true. This is the epistemic sense of proposition. So you assign an estimation about how likely it is that something's actually true. Or there's a probability that a particular event will happen. So that's sort of an objective sense of thinking about probabilities out in the world. So the first one is your estimate in the head for whether or not something's true. And the second is the probability that it happens in the world outside of the head, in fact, in reality. And what happens is that logicians and epistemologists and philosophers usually talk about propositions. Statisticians tend to talk about events. That is, they talk about these two different ways. Don't be confused by that. There's no substantive difference for us. One way can be translated to the other, and I'm going to typically switch back and forth without making a distinction. But you should think, for at least now and in later courses when we talk about this, we start wondering about what the metaphysical nature of a probability is. Is it a thing that exists out in the world, or is it just a subjective sense about something's maybe being true? And that matters for some high level theoretical issues in philosophy of science. We don't need to tackle those. Okay, so we're going to adopt. I've been saying we're going to build a formal model of propositional logic. We're going to adopt some conventions from deductive logic. So since events are represented by complete propositions, we will only be using the language of propositional logic. And the way you do that is a proposition is a single complete subject and verb sentence. And we will represent propositions, or usually sentences, by a capital letter, A or B or C. So then we use some logical connectives. So the major logical connective is the tilde or the not. So the negation of a sentence has the form of not A, and it's represented in propositional logic as tilde A. And that little squiggle is up in usually the upper left-hand corner of your keyboard. And what that means is not A. So A or not A has to be true. Disjunctions are or sentences where we say that either one thing is true or another is true. So they have the form of A or B with two complete sentences on both sides. And usually in deductive logic, depending on which system you're using, we'll use the little V to represent the or. So we will write it parentheses A, capital A, little v, capital B, and parentheses. And that says either A or B is true. Conjunctions are sentences of the form where we conjoin or add them together. We say that and is A and B are true. So A and B is represented by parentheses, capital A, ampersand, capital B, end parentheses. So I'll use the ampersand usually in class or in lecture to represent and in that case because sometimes we're adding as well. Okay, so examples. So if we want to talk about the probability that a certain suit of cards will be dealt from a deck, we can say. So imagine you've got a well-shuffled deck of cards, you're about to pull a card out, and we want to know what's the probability that that card will have a particular suit, where a suit is clubs, hearts, diamonds, or spades. So we might say C, it means a club is dealt, S means a spade is dealt, D means a diamond is dealt, H means a heart is dealt. So then we'd ask, what's the probability that we get a club or a spade? We might ask, what's the probability that the card we draw is not a diamond? What's the probability of the card that we drew is a card and a heart? I mean, sorry, a club and a heart, which would be, if you're thinking ahead about that, would have to be 0 because those are exclusive probabilities. Okay, so some more conventions about the situation, about the way we represent probabilities, and this could have been done in a number of ways. It's done differently in some systems, but pretty widely spread most people adopt this set of conventions from Kolmogorov, who wrote the seminal work on this. He's a Russian mathematician, wrote it in 1933, Foundations of the Theory of Probability. So we represent probabilities by saying capital P or PR. I usually write PR and then parentheses. All probabilities will fall between 0 and 1, inclusive. So something could have a probability of 0 or a probability of 1. That is, for any proposition A, the probability that A is true is either greater than or equal to 0 or it's less than or equal to 1. Written out formally. In deductive logic, we're only interested in true or false, 0 or 1 at the ends of the scale. But in inductive logic is the signs of claims that are less than certainly true or false. It's everything in between, and that actually has to do with almost everything in your life. It's very rarely the case that anything is absolutely certainly false or certainly true. We're usually operating with very, high probabilities or low probabilities or something like that. If a proposition has probability 0, then it's false. If a proposition has probability 1, then it's true. If A has a probability of 0.4, then we say that A is 40% likely to occur or 40% likely to be true. If A is probability 0.85, therefore it's much more likely to be true. It's going north of 50. And anything over 50, as we learned before, means it's probably true. It's improbable if it's below 50. It's probable if it's above 50. And the higher it goes above 50, the more probable it becomes. So 99% certain is a very high degree of probability. Now, another important basic logical connective we got to understand is that in English, the way we talk, we use the same term or, but it has two different uses. It has an inclusive sense and an exclusive sense. And usually we figure it out by context which one we mean, or by experience we know which one somebody means. These will be immediately obvious to you once you see them. So the inclusive sense means either one or the other is true, or possibly both. So sometimes when we say or, we mean one or the other is true, or maybe both are true. Say, if your grandmother or your grandfather had heart disease, then your chances are higher. And that includes the possibility that maybe both of them had heart disease, and that might make your chances even higher still. Studying inductive or deductive logic will improve your LSAT scores. Either one will help, or both will certainly help. Going to a Giants game or an A's game will make your dad happy, and going to both would make him very happy. So those are examples of using or in the inclusive sense in English sentences. The exclusive sense means one or the other, but not both. And we're going to focus primarily on that in these early discussions. So we're going to use or in the exclusive sense. You can vote Republican, Democrat, or third party. And I should point out that a disjunction can have as many disjuncts as we like. So this one has 3. They're mutually exclusive. One or the other or the third has to be true, but not all 3 or not 2. So disjunctions can have more than 2 disjuncts. You can get the baked potato or the French fries with your sandwich, but not both. We can either go to the opera or the monster truck rally on Saturday night, but you can't go to both because they're at the same time. So those are mutually exclusive examples of or used in English. And we're going to think about mutually exclusive events for probabilities mostly. So mutual exclusivity means 2 events A and B are mutually exclusive if they cannot both happen at once or both be true at the same time in the epistemic sense. So for example, you can't get both heads and tails on the same coin toss. She can't both pass and fail on the same assignment. You can't hit a single and a double at the same time at bat. He can't both be paying and not paying the tab. One or the other has to be true. For now, we will be focusing on how to determine probabilities in the exclusive or cases. All right, so let's think about a few of those. We could use a Venn diagram to represent a deck of cards. So there's a full deck of cards, and we draw a couple of circles to represent the black and the red cards. So let's draw a random card from a well-shuffled deck. What are the probabilities that you'd get a black card? Well, that's 26 out of 52, which is 0.5, 1/2. 1/2 of the deck is black. So the odds of getting a black card are 0.5. What's the probability of getting a red card? Again, it's 0.5, 26 out of 52. What's the probability of getting a black or a red card? And in this case, we add those together. It's going to be certain, you're certain to get black or red because that covers all the possibilities. What's the probability you get a black and a red card? That's 0 because those are mutually exclusive. Cards are either black or red, they can't be both. Okay, so those are pretty simple. Now, let's talk about how do we compile probabilities in these kinds of cases. So a sentence with an or is a disjunction. And here's our rule for mutually exclusive probabilities. If we're trying to figure out the probability that A or B is true, well, what you do is that equals the probability of A added to the probability of B. So you simply add them straight up. That's what we just did in the last case where I said, what's the probability that it's a red or a black card? Well, that has to be 0.5 plus 0.5, which is 1. What's the probability that the card I drew is a club or a heart? Well, clubs make up 25% of the deck, 13 out of 52, and hearts make up 13 out of 52 of the deck, 25% of the deck. So the probability that it's club or a heart is 0.25 plus 0.25. So there's an application of the addition rule for mutually exclusive probabilities. What's the probability that I will roll a 1 or a 2 or a 6 on a 6-sided die in one roll? Well, the probability of one of those is 1/6 because the 1 on the die is 1 out of 6 possible sides. So the probability of getting 1 or 2 or a 6 would be 1/6 plus 1/6 plus 1/6. And the rule there for adding fractions is just to add the numerators as long as the denominators are the same. So that makes out to be 3/6, which calculated out as a decimal is 0.5. Okay, so let's think about some non-mutually exclusive probabilities, cases where the probabilities overlap. Things get a bit more complicated. We have a different rule for those kinds of cases. So this is a complicated example. Consider an urn filled with 50 balls and 50 cubes. And all of the balls are red, all 50 of them. Half of the cubes are red, and half of the cubes are green. So question, suppose we are just interested in representing the relation between the set of red objects and the set of balls. So I'm drawing circles here in this Venn diagram. Does that accurately represent the set of balls and the set of red things? And we haven't learned about formally about how to draw Venn diagrams, but there should be something suspicious about that. There's something about that picture that should strike you as not being congruent with what got said in the sentences above. All of the balls are red, and the circle capturing the circle representing the red things is separate or distinct from the balls. So there's something wrong with that picture. It can't work. Is this a correct representation? No, there's something wrong with that representation. We've got an overlap of red things and ball things. This is a better representation. So we need to represent the two circles as intersecting as following. So there's 75 red objects. All of the balls are in the red circle, and 25 cubes are outside, they're green. And this is not formally represented like a Venn diagram, but it lets us sort of conceptually see what's going on. So there's 25 things in this case that are not balls, but they're red. And we need to capture those. We did in the previous example. So question, what's the probability in this case if I reach into this urn that I'm going to draw a red thing out of the urn? So there's 100 objects, 50 balls and 50 cubes. And how do we figure out the probability of getting a red thing? Well, you can look at it and just see that since there's 50 balls and 50 red balls and 25 red cubes, there's 75 red objects in there out of 100, so it's 0.75. What's the probability I'm going to get a ball? Well, there's 50 of those out of 100, so it's 0.5. What's the probability I'm going to get a ball and it's red? Well, that's just the same as the probability of getting a ball. Why? Well, all the balls are red, so asking what's the probability of getting a thing that's a ball and it's red doesn't add anything to the probability. This is an example of non-mutually exclusive cases. I'll show you in a second. What's the probability of getting a ball or a red thing? And this one's a bit trickier. Maybe intuitively you can see it. I'm going to give you the rule in just a second. So the probability of getting a ball or a red thing. Well, there's 75 red things. And the probability of getting a ball doesn't add anything to getting a red thing. So it's just equivalent to the probability of getting a red thing, 75 out of 100. Okay, so the rule here, put more formally, that you're sort of doing intuitively in this case, is called the addition rule for non-mutually exclusive probabilities. And the way it works is if we're looking at non-mutually exclusive cases, not like our card cases or our coin tossing cases, but like the case I've constructed here, the probability of getting of A or B's being true equals the probability of A plus the probability of B minus the probability of A and B. So that's formally how we insert the numbers into the rule to get the right answer that you sort of intuitively figured out in those last two examples. And I'll show you some more cases to illustrate. So in that last example, what's the probability of getting a ball or a red thing? Well, inserted into our rule, the probability of a ball plus the probability of getting a red thing minus the probability that it's a ball and it's red. So written out, that means 0.5 plus 0.75, which would be 0.125, minus 0.5, which puts us at 0.75. Okay, so I'll make a point here that if you ever get an answer to a problem in a probability example or homework assignment or anything that's over 1, notice from the convention we adopted that all probabilities fall between 0 and 1. If you ever get an answer that's over 1, then you've done something wrong. So notice that what happens here is that if I simply add the probability of getting a ball to the probability of getting a red thing, I get 1.25. So that can't be right. I've double counted. I've double counted half of the red things. I've added more red things to the 75% in there by double counting. So with this minus 0.5 here, the probability that's both A and B, we back that out, we subtract it out, and we get back down to 0.75, which is the right answer. It's the one you can see intuitively. But formally, this is how the answer gets written. Okay, so some more examples. A deck of cards has 4 suits: clubs, diamonds, hearts, and spades. There are 52 cards in a deck and 13 of each suit. What are the probabilities associated with drawing the following from a well-shuffled deck? The probability of getting a club is 0.25. That's 13 out of 52. The probability of getting a diamond or a heart is 0.25 plus 0.25, which is 0.5. You should see how that's an application of the addition rule for mutually exclusive probabilities, because diamonds and hearts are mutually exclusive. What's the probability I get a diamond or a heart or a club or a spade? Well, that's a certainty. You have to get one of those. So it's 0.25 plus 0.25 plus 0.25 plus 0.25, which equals 1. What's the probability I get a non-spade? Well, non-spades are the hearts, clubs, and diamonds. That's 75% of the deck. What's the probability of getting a not diamond or a club? A not diamond or a club? Well, the answer here is 0.75. Note that we subtract here because the answer cannot be 1. And being a club doesn't add any probability to being a non-diamond. That's redundant. We're double counting. They're non-mutually exclusive. So if you apply the rule for non-mutually exclusive probability addition, you'll get this answer, 0.75. So here's that example illustrated a little more explicitly. Since all clubs are non-diamonds, the best way of picturing this example is this way. So here's the class of non-diamonds. Clubs all belong inside of there. There's 13 of them versus 39 versus a total of 52. Since in the case the probability of being a club can't add anything to the probability of being a non-diamond, we write it out this way. 39 out of 52, or 3/4, 0.75. And what I've done there is I've just done shorthand for the addition rule for non-mutually exclusive probabilities. But if you plug in all those values, as I showed you with the rule, you'll get this 0.75. I should have done it in this example. Okay, so some more cases. A single-sided die has 6 sides numbering 1 through 6. Assume all sides have an equal probability when rolled. You don't have a trick die. Question, roll it once. What's the probability? What's the probability of getting a 1? Well, that's 1/6. What's the probability of getting a 1 or a 2? That's 1/6 plus 1/6, which equals 2/6, which reduced is 1/3. And let me just say that when we write these out as a decimal, 1/3 is 0.33 repeating, or 1/3. I'll take either one of those as an example. But notice that if you, for repeating decimals like this one, 0.33 repeating, if you don't write that out or capture it as 1/3 in your homework, you may lose decimal places out there in the 4th or 5th or 6th place. I'll show you some examples later where that matters. But for now, representing this probability can just be 0.33 or 1/3. What's the probability you'll get an even number if you roll this die? It's 1/6 times plus 1/6 plus 1/6, which is 1/2. What are the even numbers? 2, 4, and 6. And the probability of getting one of those is 1/6. So you add those together since they're mutually exclusive. What's the probability of getting an odd number or getting a 2? Well, the probability of getting an odd number is 3 out of 6. And a 2 is not odd, that's another 1/6, which adds up to 4/6, which is 2/3. What's the probability of getting odd or even? That's the totality, that's 1. What's the probability of getting an odd and an even number? That's 0. These are mutually exclusive. What's the probability of getting a 5 or an odd number? And this is a case where I think that may be represented wrong. That's actually wrong. Probability of getting a 5 or an odd number is just 1, 3, and 5. That would be double counting, so I've got the wrong answer there. The probability of getting 5 or odd is just 1/2 because we don't want to double count the 5. So disregard this answer. I've got this wrong. It's actually 1/2. It's not 2/3. Okay, so our summary so far then is we've learned a couple of rules. Probabilities of propositions or events occurring, we've learned about that. We've learned the formal conventions, letters for propositions using the tilde, the ampersand, the or, the parentheses. We've learned about the inclusive and exclusive senses of or. And we've learned the addition rule for mutually exclusive events, and that's written out this way, and it gives us the guidance for how to compile those probabilities. And we've seen a couple of examples of the addition rule for non-mutually exclusive events, where we add the two and then subtract out the overlap or the extra or the double counting. And I'll show you more examples of those in part 2 of this lecture about Hacking's chapter 4.